So let's discuss a little bit about this tunable model. So this tunable model has really evolved over many generations. So in the earliest days of statistical learning, this tunable model is really simple. So for example, M versus X, in the most classical case, is just a line. Okay, so theta depends on theta is basically the slope and the intercept of this line, right? Theta is just this linear model, and this line is equal to y is going to be equal to ax plus b. So this is really the oldest machine learning model you can find in really the history of statistical learning. Basically, I have a linear model. That's the simplest thing I can use. Okay, and time has passed, and although this is still used a lot, we have invented other ways to parameterize models that solve a larger class of problems. So, for example, we have invented neural networks. And neural networks is essentially not just a simple a model, but a chain of models. So giving the inputs X, usually we involve a matrix multiplication. Basically, X usually involves X is usually a high-dimensional input. For example, an image or even a video, right? An image contains usually hundreds or thousands or even millions of pixels. A video would even involve more pixels because you have pixels in every frame. So you multiply this with a matrix or a convolution, right? A convolution is really one way of saying, describing a sparse matrix. So this is going to give you some intermediate result. And the intermediate result is going to be fed into some kind of a nonlinear function, right? A nonlinear function may be as simple as a function that's 0 when the input is negative and just equal to the input when the input is positive, right? So that's the most one of the most commonly used nonlinear functions out there. And the nonlinear function may be parameterizable, may be not parameterizable, such as in the case of ReLU. And that, in fact, the output of this nonlinear function feeds into another matrix, and this another matrix produces output, feeds into another set of nonlinear functions, and etc. Right? So how many of these things, how many of these layers you have basically determines the depth of your neural network. And this fancy phrase of deep learning basically means constructing a neural network that has many different layers. Okay, and for every matrix or convolution layer you have, the entries of the matrix or the kernels of the convolution are completely tunable. So all of these matrices are thetas. And sometimes the nonlinear functions also involve parameters that you can tune. So all of the set of entries in the matrices and the parameters in the nonlinear functions of every layer comes together to form your parameters of the model, theta, right? So as opposed to the linear regression case, in the linear regression, if I have an n-dimensional input, I have n+1 parameters. In the deep neural network case, the number of parameters can potentially be a lot more. Okay. And we have yet something that is even newer in some sense. That is the class called physically informed models. That usually involves some kind of a differential equation or some kind of a physical model that describes a system derived from physics. And you actually parameterize the unknown things in your model, right, into theta. So one of the examples is a weather forecast. So you have actually a pretty good set of differential equations that tells you how the weather, how the atmosphere evolves. But there is still a lot of unknowns, or still a set of things that are too complicated to describe completely using first order principles. Things like turbulence or cloud, or the effect of trees on the ground on how much does it slow down trees or slow down winds, or how much evaporation, how much moisture does trees provide into the atmosphere. So these are the unknown things that you're going to be all lumped into theta. Theta are the tunables in physical models. Okay, so all of these cases basically can be described using a function, m as a function of inputs and tunable parameters theta. The idea is that I want to optimize, I want to minimize over all the possible thetas some kind of a metric norm between let me also first write a summation here. So I want to minimize for all the possible, for all the training data. I goes from 1 to n, right? N is the number of training data, a certain metric of the difference between mxi theta minus yi. Okay, so that's the typical regression. So this is a regression as optimization.